Yeah. Thank you. Yeah. Thank you so much for coming, and I'm very happy to have the opportunity to talk here. So today, I'd like to talk on the derivations for multiple zeta values. There are several classes of linear relations of multiple zeta values which conjecturally give the old relation. One of them is double shuffle relation. So today we will focus the double shuffle relation. So here is the outline of this talk. So double shuffle relation. This is one of the class of linear relations between multiple zeta values with rational coefficient. So here is the double shuffle relation. Exactly speaking, this class doesn't give all relations, so we need to extend more. So extended one. Conjecturally, this extended class supplies the all relation of zeta values. So conjecturally, this class all relations. So today we'll focus this extended part. Actually, today, first we introduce another class of relations, so-called derivation relations. Relations. And we see extended double shuffle relation is a union of usual double shuffle relation and this new class, derivation relation. So derivation relation is contained in extended double shuffle relation. First, we prove this one today. Actually, keyword of this talk is derivation. So in this talk, we introduce three derivations, different derivations defined on some algebra. First one describes the derivation relation. Second derivation related to the shuffle product of zeta values. And the third one is correspond to the shuffle derivations. So today we see the three derivations and how they connect. So we introduce several, actually three derivations in this talk and see how they connect. By looking at corresponding automorphism via exponential map. In general, derivation and morphism, automorphism has a one-to-one correspondence via exponential logarithm map. So we look at the relation among derivations by looking at the corresponding automorphism via exponential. So corresponding automorphism. Yeah, exponential. So all results in this talk, you can find result in the reference, my paper with Kaneko and Zagie. Okay, so let me start from the definition of zeta values. Don't you mind? Is it okay? In my notation, multiple zeta value is defined by this way. Where k, all k is a positive integer, and the first index should be larger than or equal to 2 for the convergence condition. And it well known, this number has an iterated integral expression along the path connecting 0 and 1. So here, xi, eta. Here we have k1 minus 1 xi, and xi, eta. Here, kn minus 1, where xi is a one form defined on p1 minus 3 point. The eta is a dt over 1 negative t. So we call
iteration is
from right side, right hand side. If
right hand side.
yeah, first we integrate this factor and repeat the integral repeatedly. The sum of all indices is called weight of multiple zeta values. So one of the main problem of multiple zeta is to find to describe the complete description of all relations among zeta values with rational coefficients. So I think it's natural to consider the vector space spanned by zeta values, where weight k is k. Here is a Q rational space spanned by zeta value. Zeta value is real numbers, but this is a obviously finite dimensional vector space. So if there are many relations among zeta values, the dimension of this space reduces from above. So there are conjectural sequence of dimensions of this space, so-called Zagier's conjecture. No, I should use. So there are many linear relations among multiple zeta values. The simplest one is probably this one, found by Euler. This is the all relation we discovered relation is respects the weight. So both sides is weight 3. This is a whole relation for zeta values of weight 4, or zeta 4 times zeta 3 1, 1 over 3 zeta 2 2, and equal zeta 2 1 1. So there are 4 zeta values of weight 4, but the space spanned by this is just a one-dimensional space. Is known. Dimension is known. I will write a sequence. But for small weight, right?
Yeah.
Just
0, 1, and 2.
1, 1, 2, 4. Wait, yeah. Only, yeah. A very small one. Yeah. Now, this is a present from Professor Nakamura. Eraser. Japanese eraser. So here's a table of dimensions. I need a 4 columns. First lines denote weight 1, 2, 4, 5, 6, 7, 8. So second line expresses the conjectural dimension of the space generated by weight k zeta values. There are no zeta values of weight 1, so k is 0, 1, 1, 1, 2, 2, 3, 4, 5. Each dimension is the sum of 2 before and 3 before. So this 5 is the sum of 2 and 3. And I will explain soon later about the double shuffle relation, but the extended double shuffle relation. Conjecturally, this class gives sufficient all relations. So sequence is same conjecturally. And real double shuffle relation is a proper subclass of this extended one. So this sequence is 0, 1, 2, 3, 6, 9, 11, 24, 36. So we have a gap in weight 3. Actually, the zeta 3 and zeta 2, 1, that identity doesn't come from the double shuffle relation. But after extending, this class contains that relation. So today we will look at the gap between this one and this one. Actually, derivation relation, which I introduce soon later, is contained in this class. So in the next section, I will introduce briefly the extended double shuffle relation and double shuffle relation. So that's section 2. Double shuffle. So I need some algebraic setup due to Michael Hoffman. Setup. So here you see zeta value has a repeated integral expression. That expression contains only two kind of differential forms, xi and eta. So we prepare the two letters x and y. Each of them correspond to xi and eta, and regards the zeta values of this form by a word in two letters x and y. So just let's check the arrangement of x and y. So this is the element. This is just a word in two letters x and y. So the word should end y from the definition or from the correspondence, and note that k1 should be larger than or equal to for the convergence. So this corresponding word start from x. Start from x and end y. So not all words correspond to the zeta values. So first we prepare the whole space denoted by German H. This is a space of non-commutative polynomials in two variables. Non-commutative polynomial algebra generated by two elements. Not every element in this space corresponds to zeta values, so we need to define the subspace. For latter use, H0, H0 is corresponding to data values. So each word should start from X and end Y. So constant term and the other part is starting with X and end Y. This is a subspace of H. For latter use, as a middle space, H1 is defined by constant term. Other term is consisting of words ending Y. And the element of this space express the Q linear combination of multiple data values. So there are evaluation map denoted by zeta. So each word of this form maps to real data values. This is Q linear map.
The empty word goes to 1.
1 to 1. 1 to 1. One.
Empty word.
Empty word, yeah, goes to 1. Empty. Huh?
Well, for the first.
Empty word means 1 in this space, right? 1 goes to 1. Yes, so it's Q linear. Yeah. What is space? So, for example, letter Y is the element of this space, not in this space. So, this space corresponds to this type of data values. This is nonsense. It's a divergent series. So, divergent multiple data values living in this space. I will use this space soon later. And sometimes this correspondence is a little bit indirect. So if you express x to the k minus 1 y, this is a fundamental block. If you denoted this expression by dk, then it's easy to see the correspondence. There are two natural products for multiple data values. If you have two multiple data values and consider the product, we have two different ways to describe the product in terms as a linear combination of multiple data values. So I will explain such product, so-called shuffle product and shuffle product. So product of data values is a story in this space, but we lift the product, each product to this formal space. One is the shuffle product. So this product is defined by recursive relation of this way: A, U, shuffle, B, V, where A, B is a letter, and UV is any word. For any word in H, we define the new product, shuffle product, by this recursive relation, U, V plus B, U shuffle. No, sorry. B, A, U, shuffle, V. That makes sense. So the shuffle product in right hand side has a smaller depths. So inductively we can define the product of this sequence. For example, x, y, and x, y, the shuffle of x, y. By using this recursive relation, we can compute this one. But probably intuitively, this is the usual shuffle. So by using these 4 letters, you can make a 6-word 2xy xy and 4x cube y. X2y. Thank you. Yeah, thank you. This product defines the commutative algebra structure on whole space H. So this becomes a commutative algebra. Oh, sorry. Actually, this product is compatible to evaluation map. So if you apply evaluation map, some side means x zeta 2 square and the 2 times zeta 2 2 plus 4 times zeta 3 1. This is true in this space. So this product is compatible with evaluation map.
And you prove it by integration by parts, or how you prove this?
To prove the compatibility. This is a general property of iterated integral.
Yeah, okay.
Yes.
Right.
Yeah.
So basically, I guess integration by parts.
Yeah.
Thank you.
And another product is called Staffel product. Some authors say harmonic product. I want to explain next. Too strong. Or harmonic product. This product is defined on H1, not on H whole space. Similarly, this product is defined by recursive relation. Here, zk is this block. And the UV is an arbitrary word in H1. This product is defined by this way, ZLV plus ZL GKU. One more term. If third term is gone, then this is the usual shuffle product, but there are one extra term. Using this recursive relation, the product is defined, and this product makes H1 commutative algebra. For example, xy. This is Z2, Z2. Using this relation, this term produces Z2, Z2, and this term also produces same term, and the last term becomes Z4. So this product is also compatible with the evaluation map. So this product says zeta 2 square is 2 times zeta 2 2 plus zeta 4 Riemann zeta values. So comparing these two result, we got a linear relation among zeta values. Such class is called double shuffle relation. So for any element or word in H naught, we compute the shuffle product and harmonic product and consider the difference. This gives the relation. So if you evaluate this one, this becomes 0 for any element W prime in this space. This is a double shuffle relation. So two examples about comparing two examples. 2 zeta 2 is same. So we got 4 zeta 3, 4 zeta 3 1 equals zeta 4. This is a consequence.
And this also follow from just some general properties of integration, or is there any more magic in it? Or
Another proof?
It's even simpler.
But
It's just the double stuff. No, he's asking how you derive these relations. Stuff full. No, how? This one. How you derive
yeah.
That's even simpler.
Like future discussion.
yeah, I see.
Yeah.
These codes which are
Yeah, this product corresponds to such. But unfortunately, double shuffle relation doesn't supply the all class of relations, so we need to extend this class more. So look at the divergent multiple zeta values. For example, zeta 1, this is nonsense. But if we think this product formally, you can compute both product, shuffle product, and harmonic product. So corresponding word is y, zeta 1, y, zeta 2 is xy. You can compute this shuffle product. So 3 letters gives 3 arrangement, yxy plus 2xy squared. Shuffle product, this is z1 and this is z2. z1, z2 plus z2, z1 plus z3. So this means yxy plus xy squared plus x squared y. So formally, if you compute this difference of shuffle product and harmonic product, then here is a divergent word. It means the word starting from y. But fortunately, we have a cancellation here by thinking difference. So difference becomes 2xy squared negative, no, I should, right, 1 minus x squared y. Am I correct? So after evaluation, we have a simplest relation, zeta 3 equals zeta 2, 1. I know this discussion is nonsense because this evaluation, double shuffle relation never claim this is true. But we can justify this argument by considering the regularization of divergent multiple zeta values. I will only state the statement of extended double shuffle relation. For W is an element in H1, so you remember this space contains a divergent zeta, and H prime is a usual H naught. Then compute the difference of two products. In general, this element may not be in H naught because W is H1. So in general, this is an element in H1. But there are some regularization map. Like, if you apply this element belongs to H naught, then we can apply the evaluation map. This is an exact statement of extended double shuffle relation where X is a map from H1 to H0. But it's known that H1 is generated by element Y over H0 by shuffle product. So in other words, any element of H1 is expressed by the polynomial in Y with H0 coefficient. So we take a constant term of this expression. So if you have an element here, constant term in the sense of this expression. So this map assign the constant term of f to each f. For example, leg sharp yxy. So this word corresponds to zeta 1, 2. The regularization of zeta 1, 2, we compute this one. First, we express this polynomial as a polynomial in y. So it's easy to compute. Minus 2xy squared. I think we compute this equation here. So this is a polynomial of degree 1 for y. So constant term is here. So this expression means regularization of this divergent zeta value is minus twice zeta to 1. Leg. Using this regularization map, we can state the extended one. It's obvious. The regularization of element of H0 is regularization map is an identity map on H naught. So this expression obviously generalizes the previous double shuffle relation when W is the element of H naught.
But the difference before regularization may not be from H0, right?
No, may not. But if W and W prime is H0, then the difference is in H0. So regularization map acts identically. Now it's time to state a derivation relation. It's a keyword. Yes.
Could you use the other regularization?
Yes.
The
Yes.
story,
Yes.
It's the same. I mean,
Same
the
situation.
Same relation.
Same class of relation.
Is it obvious or clear?
It's not obvious, but we can
But it's
prove.
true.
Yes. Yes. So regularization map exists according to depending on each product.
Yeah.
So we have two regularization map, but two class defined by each
So if you
statement
put
is
star
equivalent.
instead of shy, it's the same.
Yeah, star version. Hmm? Oh, like this. Okay, in the next section, I want to define the derivation relation, which is described by derivation on this algebra H. Section 3. I can state right now. So this is derivation relation. So general form is proved in IKC. And when n equal 1, I will explain soon later, is proved by Hoffman. After looking at Hoffman's result, Kaneko, the second author, find a generalization of Hoffman relation. That was a derivation relation. For any positive integer n, define the derivation on this algebra. So don't confuse, we have many products on H, shuffle, staffle, and usual non-commutative concatenation product. So this derivation means derivation for concatenation product. So this means derivation means the Q-linear map satisfying Leibniz rules with respect to concatenation product. Non-commutative product. So note that H is freely generated by two letters x and y. So if we fix the image of derivation on generator, the derivation is uniquely determined. So we define image of one generator, and it's almost same negative by this. This is a homogeneous degree of weight n plus 1. It's a bit artificial. Anyway, we define derivation by this expression. Then the image of this derivation gives a relation. So apply this derivation to any element of H0. So this is an element in H0, we can prove. Then we can, after evaluation, this becomes 0 for any n. This is a derivation relation.
They somehow should follow from these extended Chapter relations, or?
That's what
Yes, I can explain.
Okay.
Let's see the example.
No, it's okay.
I'm sorry. For example, when n equal 1, it's a Hoffman relation case. Del 1 sends x to xy, and del 1 y is negative xy. Is okay? Yeah, power is n minus 1. So if you compute the image of xy, xy is the element of H node, then using Leibniz rule, so now we are in the non-commutative world, so should carefully the order of product, then x, y, y. Here is minus xy, so negative x square y. So derivation relation says this is a relation. Beta 2, 1, negative beta 3. one more example. X square y. I just paste the result. If you compute, you get this result. This corresponds to zeta 2, 2 plus zeta 3, 1, negative zeta 4. So any element of H naught gives the relations. So this is also large class of linear relations. In the next section, I want to sketch why this derivation contained in extended double shuffle relation. Section 4. So extended double shuffle relation. Conjecturally, this gives all relation contains derivation relation. This section is a little bit technical, so I try to, I don't go to the detail, but not to lose the whole picture. So, but it's quite interesting. We introduce another derivation associated to product, shuffle product and harmonic product. So if you define the map D by defined by dw is defined by the difference, w negative yw. So H has a 3 product: shuffle, shuffle, concatenation. So we think the difference of shuffle and concatenation with specific element y. Then D becomes the derivation. You can check the Leibniz rule using the recursive relation of shuffle product. If you compute, you can check the value on generators. Dx becomes 0, xy. This is y square. So D adds a degree 1 on each element. It's interesting. This is a shuffle side story. We defined another derivation with respect to harmonic relation, shuffle harmonic product. The map. This side defines not only one derivation, this is a series of derivation defined on H1, defined by you can guess the definition. Consider the dn shuffle w negative dnw. So we look at the difference of harmonic product and concatenation product. This map also defines the derivation. Derivations for any n. You can compute the value on generators. Image of x is 0, x plus y, x and minus 1y. So we have three class of derivations, three. So question is how they relate.
Is it necessary to compute to show that this is derivations?
Yes.
Or,
Yes. The recursive relation of harmonic product shows first del n is derivation. And first del n is a derivation on H1, but we can extend the derivation to whole space H. After extending, we can compute the derivation on generator xy. How derivations? So we have many derivations. Del n, this gives the derivation relations, and one is derivation associated to shuffle product, and last one is for shuffle product relates.
But they're all derivations for the non-commutative product, right? For which multiplicative structure are they derivations for the non-commutative one?
Every
All
is for concatenation.
okay.
Non-commutative concatenation. There are beautiful relations between these three derivations. First, we think that sum of derivation is derivation, so this is also derivation. But here is an infinite sum, so we need to introduce a more larger space derivation on her hat. This just means the formal power series into variables. Derivation. Also, del is similarly del n, and this is also derivation. So now we have three derivations without subscript: d, n, round d, and delta. Now we look at the corresponding automorphism of three of them via exponential map, then the relation is clear. This is a theorem. Exponential of d. So exponential of d means n factorial d to the n rather than 1. This is a definition, and this is a general fact. The derivation, precisely speaking, unipotent derivation on this non-commutative formal power series algebra corresponds one-to-one of an exponential map, the automorphism group of H unipotent. So our element, so H del delta T is an element of this space, but we look at the corresponding automorphism rather than derivation itself.
Maybe there is also completion on the right hand side.
Ah, thank you. Then exponential, so this is the automorphism. Becomes exponential. There. I think it's beautiful formula. So each automorphism corresponds, so this first factor corresponds to shuffle product. This second automorphism for shuffle product, and this one derivation relation. The proof is just a computation. So, wait, ED, this notation is better. E delta E E. The image on X and Y. Note that H hat is also freely generated, topologically freely generated by X and Y. So image of X and Y of automorphism determines
Automorphism, algebra.
algebra automorphism. Yeah. Algebra is determined by the image on generators. So I computing the image of X under this map. To compute such element, in many cases, first we compute the nth composite of derivation, then compute this sum. Sometimes, so I computed this element by standard way. So here X is 1 minus X minus Y, inverse Y. But in general, it's not easy to compute the image of generators.
Sorry, maybe I don't even understand the statement of the theorem, because X both these things are automorphisms of different algebras. So what? No. But one is for shuffle. One for
No.
They're different.
They're all for concatenation.
Concatenation.
Oh, they are
Concatenation. Yeah. So derivation and automorphism respective.
Oh, I see.
Concatenation. For non-commutative concatenation product.
So automorphism is the root of fundamental completion of fundamental root of P1 minus L1.
Yeah, yes. Another interpretation for H hat. So it's a formal computation. But to compute this image is not easy. Actually, Zagier did. If you look at the element, you may think it's not so difficult, but actual computation is not easy. So as a comment, in general, it's not easy.
They don't seem to fit. The formula. They
Yeah.
don't seem to fit in the formula, so if you read out,
You distribute
shouldn't they somehow multiply?
To show this relation, using this, first we compute this table, then just compute the image on generator. So substitute.
Oh, yes, there is substitution.
How to say?
Ah,
This is just a composition.
Composition.
So using this one, you can check.
Partial n
Yes.
and delta n.
Yeah.
For each n, they commute to each other.
Ah,
Otherwise, it's very difficult to compute this
Ah.
expression.
This is non-commutative.
No. I mean, delta n.
Yes,
and delta
as a derivation. So you mean the bracket.
No, delta n and delta m. Partial delta n and partial delta m.
So you mean this one?
Yes.
This is commutative. This is commutative.
Otherwise, the summation and take explanation, then it's quite
Yes.
messy.
Yes,
It
yeah.
is impossible to compute.
Yes. So this series is commutative each other, and the del n is also commutative. But the del n and round del n is not commutative, but satisfy a simple some bracket relation. So one of the problem is the D algebra generated by such derivations structure. So before going to the last part, this is a homework. Actually, it's advanced homework. If you define the derivation D, for example, xy, define derivation by this equation, this is a derivation. Then what's the exponential image of this derivation? It's very difficult, so I should write the answer. X of image of x is easy, just 1 minus x inverse x. But this is a problem, it's complicated. Answer becomes 1 minus x minus 3y inverse 1 minus x. This is the answer. So there are no cancellation here because it has no commutative. So in general, it's quite difficult. So as far as I know, I think there are no general procedure to get the corresponding exponential. But if derivation is quite simple, this is not simple, but rather simple. In this case, we can compute such explicit description. Okay, let's go on. The last part. So using this identity, we can prove derivation relation contained in the extended shuffle relation, double shuffle relation. So this is a key identity. No. So I want to put a name. This is delta. So this is an automorphism. So definition delta is composite of two automorphisms. This one is a definition delta. Then next theorem is delta gives a relation. Actually, delta minus identity map. This is a map, not automorphism, but if you compute the image of this map on H node, then this gives a relation of multiple data values. So technically, so this element is a power series. So this zeta should be applied to homogeneous part wise. Wise. So this is a sketch of blue.
So bracket is another bracket.
Bracket means
After zeta, another D.
That's more, right? So one more. This one. Yes. First compute the power series, then apply the evaluation map.
If you choose an element in H0 with certain degree, then you apply delta minus identity, then the higher degree contribute only.
Yes. So yeah. In general, this is a power series. So we should apply
you apply this
zeta in
after-
each homogeneous part. Then each homogeneous part goes 0.
So almost identity delta delta minus identity.
Yes, yes.
Or only the degree is same, but it affects something. I'm sorry.
No.
Delta, the homogeneous delta is a ring automorphism.
Yes,
Ring
yeah.
automorphism. The degree zero part of delta is identity.
Yes.
I see. So that is nothing but delta, but only choose higher part.
Yes,
degree
yes,
part.
yes.
H0 is stable by delta. This
H0 is stable by delta. It's true. I didn't mention, but it's true. Every automorphism preserves the H0 and also H1. So here is a rough sketch of proof. So from the definition of derivation D and delta, so this shuffle product and the shuffle product, we can prove for any element in H node this one expressed by first we can prove this one from the definition of D. And similarly, we have a similar formula with this, by exchanging D and delta. 1 plus y, y harmonic y. This is true for arbitrary element W in H node. And so you see the similar element here and here. So we want to consider the difference to relate the double shuffle relation. By combining these two operators, these two identities, we have this formula. Sorry, this is D. This is negative delta. So first identity says the shuffle product with some specific element, power of y, is controlled by some automorphism. The second relation says the harmonic product with power of y is controlled by some automorphism. So by combining these two formula, we can rewrite the shuffle product by shuffle product. So this is a key identity.
So, sorry, again, this is for the concatenation product. If I do e to the minus d w w prime, I get the product.
Here
So
is
if I replace w,
this mean here.
no, upstairs, if I do e to the minus d w w prime, I mean the concatenation of these two. If I
Yes.
replace w by w w,
Yes. Yes.
I get the
Yes.
concatenation of these
Yes,
two
yes.
things.
If I write this way, this is concatenation. So this expression means it's also for concatenation.
Yeah.
Taylor expansion y square, y cube is
of
also. Then we compute the extended double shuffle relation of this form. So we extend, I didn't mention, but we extend the shuffle harmonic product to H hat, complete version. So from the extended double shuffle relation, this gives a relation because this element is an element in H1 and the W is the element in H0. So this gives a relation. But using this key identity, so shuffle product is replaced with shuffle product. negative, sorry, so this is the delta. So now we have only shuffle product inside. And I didn't mention, but from the definition of Regu-Shah, it's obvious Regu-Shah is a homomorphism for shuffle product. So we can simplify this expression by and here is the identity, and here is delta. And it's easy to compute the regularization of power of y. It becomes 1. This is from direct computation. So this computation comes from y shuffle n. N's power for shuffle product is n factorial y to the n. This computation, this is 1. This is 1. So eventually we got this expression is this one. So after applying evaluation map, the left hand side becomes 0 because it's from the extended double shuffle relation. ID minus delta H0 equals 0. So this is a rough sketch. Proof. No. I erase the key identity. Let me write down again. So ED. So we proved left hand side gives a relation after subtracting identity map. So consequently, right hand side also gives a relation. So derivation relation follows from double shuffle relation. Extended double shuffle relation. This is derivation relation. So from this identity and the previous theorem, extended double shuffle relation contains. Today, almost content which I want to say is finished. So as just a comment. So today I show the story extended double shuffle relation contains derivation relation. Derivation relation. But we can prove more extended double shuffle relation and double shuffle relation, derivation relation. If you add the usual double shuffle relation, these two classes agree. This is a final conclusion. So today, I only show the story. This class is contained in this space, but we can prove more. So in today's story, so derivation was a key word. There are 3 derivations related to the extended double shuffle relation. And I think that I don't know why such a situation happened, but the expression is beautiful. And still, I'm interested in the computation of such non-commutative power series. I'm happy if you have interest in it. Thank you so much.
Any questions?
Yeah, actually, I have a story. So, in proving this shuffle relation, you use this property of integration by parts.
Yes.
In proving this
Staff
relation, you somehow rearrange summation somehow.
Yes, yes.
And improving this derivation relation, how you prove it?
No, this is the proof, one of the proof.
Yeah, I know, but somehow in order somehow to interpret what you say,
I don't know.
Yeah.
We don't know the interpretation. So at this moment, derivation is a little bit artificial.
So you somehow don't know how to prove it, starting from a zeta function. You just, I mean.
I don't know such a method. We have no method to prove the derivation relation. One is this one, and one is which can show the equivalence with derivation relation and known other relation, so-called Ono relations. So, but that method is also probably it doesn't explain.
Well, as far as I
Question.
understand, his question is following. What you explained that this is just algebra. Behind this is any analytical, new analytical method?
No. Only algebraic. This kind of method is known.
So, I mean, this is still the same question. So you have this zeta function, and you extract some properties, using this property of proportion by parts, summation, and now you manipulate somehow. Do you have some others, let's say maybe analytical, I don't know, how to say something about zeta functions, or only these two methods are available?
In my understanding, shuffle product and Stafford is a twin, but derivation relation is not the same class. It's just the gap, plays the gap part of this way. So derivation relation doesn't relate directly the product structure. So in some sense, this is a special relation. I can say well.
You said derivation relation plus Ono.
I said derivation relation, and probably I should say precisely weak Ono is equivalent, or we can Ono is equivalent duality plus. I didn't say duality today, but these two are same. It's proved. Ono relation is another class of relation. Actually, we can state Ono relation using derivation, another derivation. We can add one more factor. Here is Ono, here is derivation relation, here is a delta Ono. Today I didn't mention this part.
So EDSR is not equal to DR.
Not equal. So this union is also not disjoint.
And here is bigger. Here is strictly bigger.
Bigger than? Yes. So you see the gap between EDS and EDS.
Sorry, could you maybe explain just the starting point, that is the definition of Dn? Why do you define Dn at all?
I think we don't know. Even though the
How did you come up with that?
so
Was it ingenious ideas, playing around, experiments?
yes. So first Kaneko discovered.
So you don't have even a meaning for Dn?
No meaning. So I said it's artificial. Very good. This identity among automorphism gives us answer. One of the answers. So derivation relation is some ratio of shuffle part and harmonic part.
Did you know? I mean, do you know if you really need all the derivations? Right? I mean, if you start by just taking the delta one, which you just to compute the dimension and see. Are you sure that delta 1 is not enough?
Zeta 1.
Yeah,
Zeta one.
delta 1. But you
delta
build
1.
an infinite family of derivation that provides for you an infinite set of relation, but you add to the usual double shuffle. But if you just put the derivation, the list of derivation coming from 1, so Hoffman relation.
Delta 1.
Yeah, so delta 1 is Hoffman relation, right?
Yeah, numerically, probably Hoffman relation, so delta 1 is sufficient to give the whole.
Sorry?
Am I right? Delta 1 is a Hoffman relation.
Yeah, Hoffman relation.
And double shuffle relation, very union, gives all relation. This is one of the
So is this
another
Yeah.
conjecture.
Yeah, okay, so it's not known yet. Okay.
Yeah.
Okay.
But
So it's possible
double
that-
shuffle relation union delta 1, is it equal to extended double shuffle relation? It is not known also.
Double shuffle relation, derivation relation means del n, right?
One.
No, one, just one.
One.
You said it's
Delta
Hoffman's
one.
relation.
Yeah.
This is extended double shuffle relation.
But if you use only partial one, the DSR union partial one is
It's already, yes.
No, I don't know. This is called or not.
But you said it's Hoffman's relation.
I see.
Yeah, but the equality was asked as a question.
Okay.
That's good.
Yes, it is a numerical
Okay.
conjecture. This is right?
in this extent, is your formalism of extended double shuffle relation equivalent to Racinel's regularized double shuffle relation?
I'm not sure, but I think so. No one checked precisely. So language is totally or a little bit different, right? They use the associator, so they are in the dual setting.
But in your talk, you did not mention anything about how to say zeta 1 is how to say almost equal to log n plus gamma. You did not use.
I didn't use. Well,
But maybe to prove this,
to prove the, so today I only explained this inclusion. In that place we don't need. But to prove the this direction we need. Or in the talk I said double shuffle extended version can be replaced with regularization for shuffle product. So to show the equivalence, we need such a regularization procedure.
Okay, so thank you again.
Thanks so much.